Hi, everybody. Welcome to Mount Moleville. Yes, this is where we learn how to do stoichiometry. Where is Mount Moleville, you ask? Well, Mount Moleville is about 2 hours west of, Wellesley College. It's a great place to go in the winter because you can ski on these amazing trails. But for us, it's really going to become our stoichiometric ski resort. So really the idea about presenting stoichiometry here is a quick review. Feel free to fly through any of these videos at your leisure to help bone up on your stoichiometry skills. And this video today is all about bunny slope, kind of down there, the green circle kind of ski slopes. That's where you first learn. So feel free to get some review there. Then we might move up to some place like, Bob's Bowl and start doing a little intermediate stoichiometry problems. And then hopefully you will finish off as this little 8-year-old does, skiing down John's Cliff. Oh, Black Diamond. Incredible little dude here. It's a lot steeper than it looks, I promise. So our goal today in this video is to start off with bunny slope and look at some problems there. And then we'll move to the next video will be the blue squares, and then one more video on black diamonds. All right. So let's keep playing with bunny slope stoichiometry problems. So really from the basics, let's just start off with what are all these symbols mean? What's going on over here? Right away, I want you to spy these idea that there are species and substances on the left of a reaction. The arrow goes to point to products that are formed on the right, and those are your products that you make in a chemical reaction. So also in these chemical reactions, you will see little subscripts in parentheses. These are telling you what these substances are in these reactions, where S means solid, AQ means aqueous, meaning that substance, specifically the one in our reaction, copper sulfate, is dissolved in water. Then you have the other ones that are not in this reaction, but you should keep a lookout for. There are pure liquids and pure gases with LNG. Then you look at the actual letters in the reaction. What's going on here? Well, this balanced chemical reaction is showing you that 2 atoms of iron react with 3 molecules of copper sulfate. And since molecules and atoms are so small, we could also scale up this ratio in this reaction to moles. Welcome Avogadro's number. Woohoo! Yes, you could have 2 moles of iron reacting with 3 moles of copper sulfate. And that just means you're reacting a whole bunch of these atoms with a whole bunch of these molecules. And again, you could use the same thing when you look at the product. You're going to make 3 moles of copper and 1 mole of iron sulfate. So that's the description of what we see here. This reaction is kind of gross. It's huge. It's got tons of stuff in it. And is it really telling you what's taking place in the reaction? What chemical changes are actually happening? To do that, we want to take this gross equation and turn it into a balanced net ionic equation. So let me show you how that happens. Compounds that are in aqueous solutions only actually have the ability to split apart into 2 species, a positive one known as a cation and a negative one known as an anion. So looking at our aqueous species on the reactant side, we have copper sulfate here. What could it fall apart into since you have 3 atoms in this molecule? To help you figure out what are the common ions that actually are going to fall apart out of copper sulfate, it's really helpful to have this common ion chart here on the left, down there. And you can find this also in our online lab manual in Lab 1. So this will help us understand that something like SO4 is known as sulfate, is a group, likes to stay as a group, and fall apart as a 2- species. And therefore, if we have 3 copper sulfate molecules, we will have 3 sulfate ions. And to make sure that our copper sulfate is neutrally charged, which is what it says in the top, there's no charge on the molecule, then I know I must have 3 copper 2+ ions to balance out the 3 sulfate 2- ions to make a neutral copper sulfate. Okay, we can go look at the product side. And again, the only little trick to this one is now that you're experts at sulfate and recognize that 3 sulfates are going to fall out of this molecule, there's a little thing that we want to be very leery of. Don't just assume that Fe2 is going to fall apart into Fe2 6+. That Fe2 is a molecule of 2 irons joined together, and irons do not like to be joined together. If you look over at the common ion chart down at the bottom over there, you can see that Fe likes to come apart in one of 2 ways, either Fe2+ or Fe3+. And so when it falls apart in this molecule, you actually generate 2 Fe3+. Okay? That's what you need to balance out the 3 SO4 2-. Cool. How does all this help us take it from a gross reaction into a net ionic equation? What we want to do is cancel out any species on the reactant side and the product side, any species on the reactant side or product side that are exactly the same charge, the same species. Has to be exactly the same. So in this situation, the sulfates are exactly the same, and we have 3 sulfates on the reactant side and 3 sulfates on the product side. They completely cancel out. When these species completely cancel out, we call them spectator ions, which means they were needed to start the reaction and grab a bottle of copper sulfate, but the real chemistry, they were just hanging around looking at everybody else doing all their changes. So we call them spectator ions. Finally, a great name for something in chemistry. And this will help us generate a much simpler net ionic equation, and it is still balanced as it was in the gross equation. Okay? Let's play. Just like any bunny slope, you got to get out there and practice. So show the balanced net ionic equation for this reaction over here. And I'm going to let you pause the video, stop it for a second, figure it out on paper, and then come back and I'll show you the answer. Ready? Here we go. The answer is I can only play with the aqueous species in this reaction. So I look at the very first one, HNO3 is nitric acid. And HNO3, I can look up in the common ions chart, falls apart into NO3-. This is a very common ion. So is H+. So this is where this molecule would like to fall apart. I'm going to go to that common ion chart as well, if I'm not familiar with these, to make sure that I split sodium hydrogen carbonate apart into a cation and anion and create only Na+ and HCO3-. These are the ions that they would like to fall apart when they get dissolved in water. On the product side over here, I got sodium nitrate, and that's Na+ and NO3-. Not a surprise, since that's what they wanted to fall apart into on the reactant side. Notice the carbon dioxide and water are gas and liquid. This is the importance of making sure you put these symbols into your reaction so that we know that we cannot split these apart. They are not in an aqueous solution and have to remain CO2 and H2O. Now, look for the species that are exactly alike on both the reactants and product side, and you'll notice I can get rid of the sodium ions and the nitrate ions. This leaves me with this balanced net ionic equation, which I often like to put with ones in front of each species. Some people do, some people don't. I like this because it makes sure that I'm aware that I need 1 mole of H+ for every 1 mole of hydrogen carbonate to make 1 mole of carbon dioxide and 1 mole of water. And now that's a much simpler equation than the one we started with, and we can start playing around with that mole ratio. If you want to play around with trying more practice problems with balanced net ionic equations, please check out these links. they'll give you more practice. Now, once we get a net ionic equation, nice and balanced, how can we use it? What do we use it for? It's got to be good for something. So it's best to use it in terms of a lab experience or a reaction on paper, that it's telling us a certain mole ratio exists anytime you want to do this reaction. For example, 2 moles of iron will produce 3 moles of copper in any reaction I do with this one. And again, assuming copper 2+ is in huge excess. Mole ratio between copper and iron. So if I gave you this question, in the reaction above, what's the maximum amount of moles of copper solid that could be produced if given 0.36 moles of iron solid? How would you do that problem? Give it a second. Now let me show you how I would do it and how all your instructors are going to do it. We are going to follow something known as dimensional analysis or unit analysis in any problem that involves multiplication and division. It allows us to keep track of the units of the problem and make sure that I don't end up with some wacky number just because I threw a bunch of numbers at it. So my way of doing unit analysis is to always start with the very first ratio, having the unit I want in my answer. So if my answer is, as you can see here, I want to know moles of copper, then somewhere in the problem, I have to be able to get a number that has moles of copper. And the only number I have with moles of copper is the mole ratio that we saw earlier. So I can stick that in and make sure that that occurs at the top of my ratio. And now all I have to do is cancel moles of iron. If I multiply it times 0.36, then you can see that this moles of iron in the 0.36 cancels with the moles of iron in my mole ratio. And notice the units I get for my answer are going to be just moles of copper. So I highly recommend you do it this way. You could also have started with the 0.36 as your very first ratio and then stuck in the mole ratio. Okay? Both are fine. Now, if I were to make this a blue square problem, oh no, we're only in bunny slope land. But just to give you a sense of blue square problem, I might have asked you this question and started with this question first. But if you can see that you can get to moles of copper, then when I ask you the same question to go to atoms of copper, then all I really need is Avogadro's number to always transfer moles to atoms or moles to molecules or molecules to moles back and forth. That's a great little ski lift that you can go up and down on anytime you want. So I stick this one in. I wanted atoms of copper for my answer. So you see what the very first ratio I stuck in the problem was Avogadro's number with atoms of copper per mole of copper. And now somewhere in the problem I need to cancel out moles of copper. I stick in this mole ratio, the moles of copper cancel. Now all I need to do is stick in another ratio that lets me cancel moles of iron. And that's the number given in the problem. And you can see now if your units cancel and you do the math correctly, multiply across the top, divide what's underneath, you should end up with the correct answer of 3.25 times 10 to the 23rd atoms of copper. That's a lot of copper. Okay? Here's another little link if you want to go play with this some more and practice some more. Now, a little segue here, molarity. These copper sulfates are not given to you as grams, but generally they are solutions of copper sulfate sitting in water. So here's the example. This is a 0.5 molar copper sulfate solution. And how do we use that if we're doing a mole ratio problem or a stoichiometry? So keep in mind, molarity is all about concentration. It's telling me how concentrated that copper sulfate is in water. It has very specific units, which is the amount of solute, meaning the actual copper sulfate. As you can see, that's solid copper sulfate, those little blue crystals, dissolved in solution. So the units are going to be moles of solute, the copper sulfate, per liter of solution. Here's my little blue copper sulfate mole per liter of solution. Moles per liter. That's what the 0.500 number represents. Okay? And now that that has moles of copper sulfate in it, I can use that anytime I'm told I'm given a certain volume of the copper sulfate solution. 1 liter of copper sulfate, pour it out, you would have 0.5 moles of copper sulfate swimming in that 1 liter. So let's play around with it a little more. How many moles of copper sulfate molecules are in 50 milliliters of 0.500 molarity or molar copper sulfate solution? Take a second, pause the video, try this one. Okay, and you're back. So again, I'm going to try to use dimensional analysis to figure this problem out. If I'm trying to figure out moles of copper sulfate, you can see that moles of copper sulfate is in the very first ratio I use. And now all I have to do is cancel out liters of solution. Well, I see in the problem I was given 50 milliliters. I'm going to include the actual conversion factor of 1,000 milliliters per liter. A lot of you will not. You are very brilliant students, and you will try to do this in your head. And in the heat of battle, you will divide or multiply or do something wrong with 1,000 mils, and your whole problem will blow up in front of you. Please, you have to write out these answers for us anyway. We want to see how you get the actual answer, not just can you think of the answer in your head. So write it out for us so that we can give you credit for canceling out liters of solution, liters here, milliliters here, milliliters here, to get the final answer in moles of copper sulfate. So you're actually doing it for us. Thanks. All right. How many moles of copper ions are in 50 milliliters of 0.50 molar copper sulfate? This one again requires you to look at how copper sulfate falls apart and recognize that every mole of copper sulfate will produce 1 mole of copper 2+ ions. So this is where, again, knowing common ions is very, very helpful. And if I were to have, just as an aside, if I were to have some other species like sodium sulfate and ask about sodium ions, recognize that for every mole of sodium sulfate, you produce 2 moles of sodium ions. So you would actually double the amount of moles of sodium ions. But for copper, it's 1-to-1. So no math needed here, as long as you can show me the ratio is 1-to-1. Cool. Again, more websites. I know you guys kind of like Khan Academy. Feel free to go there. But Chem Team is another website that has a lot of good stuff on it. I hope you enjoyed this video. After you become a green circle skier, it's upward and onward. Here we go on to blue square intermediate. Yeah. See you later.